Okay, for those of you who intend on careers in some kind of engineering, particularly mechanical or civil or aeronautical, this is going to be vocational training for you. And so, really pay attention, and also the techniques I'm going to show you today are real skills. So the first time you do it, most of you aren't going to be very good at it, but that's okay. Just keep practicing and practicing and practicing and practicing. There's no substitute for just working lots and lots and lots of tedious problems. But pretty soon, after working lots of problems, it becomes second nature, and you start seeing the world in a Newtonian way. And that's actually the way to see the world. Sometimes our common sense fails us. Let's review first Newton's laws. So let's review a little bit. We had his first law, which was the law of inertia. Now, I'm not going to write out the whole thing here, but it basically says objects don't change the way they're moving unless you force them to do so. So if an object is moving through space with a constant speed and constant direction, if there's nothing in that space to apply a force to it, it will just keep moving forever. Or if an object, like this pencil, is at rest, at least compared to our reference frame here in the room, it's just going to sit there. It's not going to change its motion. Are there forces acting on that pencil? Yes. The table is pushing up on it, the ground is pushing down on it, but there's no net force. There is no net unbalanced force that is making this pencil accelerate until now. Okay, so now the second law basically is a law of acceleration. Now, when we did kinematics in the first few chapters of the book, we described what acceleration is, and we had some equations that described how objects move through time and space, but we didn't describe why things accelerate. And this gives us an equation that basically says that the net outside force acting on an object will cause an object to accelerate. And the force and the acceleration will be in the same direction. And the force and the acceleration are directly proportional to each other. If you double the net force on an object, you will double the acceleration on it. Okay? But the amount of acceleration depends on how much stuff you're trying to accelerate. I mean, right? The bigger something is, the more mass something has, the more difficult it is to accelerate. So it's also directly proportional to the mass. And here we get F equals ma. Many of us consider this the most important equation in all of physics. Because it applies, it basically is the foundation for engineering. My son's in a class right now called statics, which is the first big engineering class, really hard engineering class that sophomore engineers take. And it's really just two equations in the whole class. Well, there's more to it than that, but the net. Some of the forces equals 0, some of the torques equals 0. Well, some of the forces is the net force. They deal with things where there is no net force acting on an object. Things like bridges and roads and structures, right? You don't want those things to accelerate, I hope, all right? You don't want a bridge to accelerate, and so that's what they deal with in a class like statics. This is where we got interrupted last time, the third law. And the third law is the law of interaction. And I wrote it down last time, so I'm just going to say it right now. The law of interaction says this: for every force on one object, there must be an equal but opposite force on another object. Okay? For every force on one object, there exists an equal but opposite force on another object. Now, here's an example. Okay? When a bug hits the windshield of a car, which experiences the greater force? The bug or the truck? They experience the same force. That's what the law of interaction says. The last thing that goes through that bug's mind, well, actually, the last thing that goes through the bug's mind is its rear end, right, as it hits the truck. But the last thing that the bug can think as it's being smashed into the windshield is, at least I'm applying an equal and opposite force. Okay? It's its last great act of defiance. Now, of course, the result of those forces are not equal, right? I mean, if you're the bug, the force applied to the bug is catastrophic, right? And the force on the truck is not even noticed. But they're still equal and opposite forces. And we're going to work with this quite a bit right now. In fact, what I'm going to do is I'm going to create what's called an interaction diagram. Now, forces, if you have a force on an object, it will accelerate. And that's Newton's second law. But first, let's take a look at a situation where there might not be a net force. Here's a really complicated situation, okay, which I'm going to draw a diagram of. Right here. Well, let's put it right here. Here's my eraser, and here's the table. I'm going to draw a really exciting interaction diagram of the eraser sitting on the table. Okay? So, an interaction diagram kind of shows all the forces that are acting. So, let me draw the table like this. Okay, so here's the table. Here's the eraser. I'll draw it bigger than it actually is, just so it looks. And then here's the ground. Here's the floor beneath my feet, and the earth is below that. So let's identify our system. The earth is part of our system. The table is part of our system. The ground, which is really part of the earth, is part of our system. And of course, we have the eraser. And let me right away erase the table because it's going to get messy. I'll just put table right there. So here's the ground, the earth, the eraser, and so on. Now, there are forces, there are pushes and pulls acting between all of these objects. And what we want to do is draw what's called an interaction diagram. And then from the interaction diagram, we're going to draw the most important picture called the free body diagram. And then that free body diagram, using Newton's second law, is going to let us solve all kinds of problems. So this is really cool. This is an extremely powerful thing you're going to learn today. All right, so first of all, the eraser, here's the eraser on the table. It's not floating away into, it's not floating, out. Why? Because something is pulling on it. Right. The Earth's gravitational field is distorting space-time. And that distortion in space-time pulls the eraser towards the center of the Earth. Okay. Now, you don't need to know all that space-time stuff. It's just a cool thing to say. Never pass up an opportunity to say space-time continuum. But okay, gravity. So that's an interaction between the eraser and the whole entire Earth. Right here before your eyes, the eraser is acting with so I'm going to draw an arrow representing the force of the Earth pulling down on the eraser. So I'm going to go F, E, oh great, Earth is eraser, and Earth, you know what? I'll put capital E for earth and lowercase e for eraser. So this is, let me zoom in. So what is this force? It's got a magnitude and a direction, right? Force has a magnitude and direction, so it's can be represented with an arrow. And this arrow represents the earth pulling on the eraser. And the earth is pulling it straight down towards the center of the earth, yes? Okay, of course it does. Now, but here's something you might not realize, because we don't notice it. The eraser applies an equal and opposite force to the earth. This eraser is actually pulling the earth up towards it. So how come we don't see the earth just slamming up towards the eraser? Because the earth has like a billion, thousand times more mass than the eraser does. Something like that. And so we don't notice its effect on the earth, but you know, it's there. So this is Newton's third law. The earth pulls down on the eraser. Now watch how I do this. This is the force of the eraser on the earth. See how I just reversed the subscripts? So this right here, the force of the earth, this is called the agent. The agent. The agent is the outside thing that's applying a force to the object. This is the agent, this is the object. So for this force, the earth is the agent acting on the object, which is the eraser. Now over here, they reverse roles. The eraser is the agent that is acting on the earth. These are just names that we use. An agent is if somebody if you made some offensive remark and so she slaps your face, she is the agent, okay, and you're the object. Your face is the object, okay, just like that. So it's so you would use these subscripts to represent that. All right, now, so if there was no table, what would happen to the eraser? It would accelerate towards the ground, right? At what rate? Yeah, 9.8 meters per second every second. So there's a force, and this is the force of the table on the eraser. F sub, okay? So look where the base of that is. This is a force acting on the eraser, and it's pushing the eraser up. Okay? Now, for every force, there is an equal and opposite force. So, what is this eraser doing to the table? It's pushing it down. So this does get, interaction diagrams get really messy. This is the force of the eraser on the table. Okay? Now I've just drawn the interaction diagram between the eraser and its environment. Now of course there's air pressure, okay, there's a buoyancy force that's negligible and all that, but we're going to ignore those things. So now what I can do, by the way, we can keep going, right? Here's the table, and doesn't the earth pull down on the table? Okay, so there's the force of here's the force of the earth on the table, and then of course there's the force of the table on the earth. Okay, so for every, there's this, and then of course there's the force of the ground. The table is not accelerating towards the earth because the ground is pushing up on it. So we've got the force of the ground on the table, but then the table, I'll just draw it over. This is really, you'll see how awful this gets. It all depends on where you draw these arrows. I've run out of room. So there's the force of the table on the ground, and it let's see. I think there's. Oh, that's good enough. Okay. So it gets really crazy. But here's what we're going to do, because what we want, you have what's called the object of interest. Okay? That is, you're going to do a problem, and what you need to do in this problem is choose the object that you want to understand the motion for. Now, in here, there's really three objects in my entire system. Here's my whole system. There's the eraser, the table, and the earth, and I suppose the ground, which is really part of the earth, but that's the contact force between the table and the earth. But what we're going to do is pick one object to be the object of interest. And here's what's really cool. You can just say, okay, we're only going to look at the eraser. So now what I'm going to do is I'm going to move from the interaction diagram to what's called a free body diagram. This is big stuff right here. Some of you will use this for the rest of your lives. Okay, I know I have, but you know, I'm a physics teacher and have to teach. But if you're you're a mechanical or aeronautical engineer, or structural engineer, architectural engineer, any engineer that really deals with forces of any kind, you're going to use this idea right here. So we isolate the eraser. So when you draw a free body diagram, you just draw the eraser. You do not draw the environment around the eraser. See, the interaction diagram shows the entire system, but the free body diagram isolates one object and then only looks at the outside forces acting on that object. So what are the forces acting on the eraser? Okay, you've got the force of the earth on the eraser, and then you have the force of the table on the eraser. Okay? Now, we can look at this object, and now we're ready to do some analysis for this object. Now, by the way, this is almost a trivial problem. So we're going to start off with the trivial, and then we're going to get gradually more and more complicated, okay? So let me ask you this. Here's the eraser. Describe its motion for me. Okay, it's not moving, but more importantly, it's not accelerating. So now what we can do, that we've drawn our free body diagram, we can now apply Newton's second law. So after you draw the free body diagram, we can now apply Newton's second law, which says the net outside force on an object will be equal to the object's mass times its acceleration. Well, what is the acceleration of our eraser? It's 0. So now, what does the net force mean? Okay, the net force means we have added up all the forces acting on the object. Okay, now we're going to do another problem here where it's not going to be this trivial, but when I add up all the forces, I'm going to add them. So that means I have to add these forces. So now let's call this a force and this a force. So it's the table on the eraser plus the earth on the eraser, and that has to equal 0 because the acceleration is 0. Oh, you know what? I meant to do this. Another way of saying the net force, okay, pay attention right now. You're going to see this a lot for the rest of the year. Now, those of you who took regular physics last year, this is old hat. But for you newbies to physics, really pay attention. I'm adding up all the forces acting on our object to get the net force. Now there's a symbol that means add it all up. What is that? Yeah, it's a sigma. I asked you because I forgot for a second. All right, this is a sigma, okay, capital sigma, I think. Sigma F equals MA. Now this is I like using sigma F instead of net force for several reasons. Sigma is kind of a cool thing to draw, okay, and it's Greek, so therefore it's pretty cool. And it also tells me what to do. It's almost like an operator. It's giving me instructions. Hey, add up all the forces acting on the object of interest. Okay, so it's telling you what to do. Add up all the force, and then that will be your net force, and that will be equal to the mass times the acceleration of your object of interest. All right, so let's go back to my vector equation. This is a vector equation. So what this tells me is this. The force of the table on the eraser is equal, but in the opposite direction, to the force of the earth on the eraser. Now, doesn't that make sense? Right? I mean, if the earth is pulling it down like this with a certain force, then this is being pushed up with an equal but opposite force. Okay, so there you go. Now, our problem is essentially solved here, or at least this is as far as we can go with this. We've taken a look at about as simple a situation as we can, and now we're going to get more complicated. But throughout this chapter 5, all the problems you're going to do, we're going to be doing the same thing over and over and over again. We're going to be following a procedure, okay? And so what I'm going to do is lay out that procedure for you, and so on. Now, one thing I meant to mention a little bit ago, and it was with Newton's second law. I think we, because the lecture last time got interrupted, I didn't mention the units for this. Let's just talk about units. In the metric system, what do we use for mass? We use in physics, in the metric system, we actually define the kilogram as the fundamental unit. It's kind of weird. Why wouldn't they use the gram? I don't know, but in France somewhere there's this slug of metal, and it's defined to be a kilogram. So at least in this class, we're going to use kilograms. And then acceleration, we use meters per second every second, which we abbreviate as meters per second squared. Okay. Now this group of units, we have a name for that, and I think you know what it is. They're called newtons, named after those little delicious little fig cakes. Okay. No, and we abbreviate with the letter N, capital N. Now, just for reference, a Newton is not very much weight, or not very much force. I mean, I've got a little apple here. It's a little toy I got at a conference. But it weighs 1 Newton. So I'll pass this around, but it's not very much. It weighs less than an actual apple because it's foam, rubber. But a Newton is not very much force. So to get a sense, you need, well, let's see, 1 pound is equal to 4.45 newtons. That's the unit conversion. So it's a little less than 1/4 of a pound. Newton is. So that's the unit conversion from pounds to newtons. I noticed that in Aaron's class, they're still doing everything in pounds and feet and inches and stuff, which is really annoys physicists. Do everything with newtons. Engineers tend to use pounds, but it's just units. You know, it's the same kind of stuff. All right, I'm going to show you a procedure for problem solving, and it has a very special title. It's called, oh dear, that was blasphemy there. I didn't capitalize it. The procedure, wait a minute, is that spelled right? Does procedure have two E's? I'm sorry, I misspelled the same words over and over and over and over again. Nothing looks right to me. The procedure, bum, bum, bum. It really needs a theme. Okay. Okay, and we're going to follow this procedure to solve a bunch of problems. And the procedure is this. Step 1. Given, find, and solve with a picture. Okay, so the first thing I want you to do when you're doing one of the textbook problems, I want you to draw a sketch of it. I want you to use given, find, and solve. And you have to draw a sketch of the problem. Okay, step 2 is draw the free, oops, it's got to be capitalized, free body diagram. So based on what they're asking for in the problem, you're going to have an object, and you're going to want to look at the forces that are acting on that object, because really what you want is you want the acceleration of the object, or you want to know what's going on with the forces that are creating that acceleration. So you have to pick that object of interest and draw the free body diagram. Step 3, choose an axis system. Okay, now X, Y, and Z. Now we usually won't need Z. It'll just be, most problems we're going to solve are going to be two-dimensional problems. Choose an axis system, and then express forces with components. So after you've drawn the free body diagram, you're going to choose your X and Y axis system, and then all the forces that are acting on your object, you're going to break them up into their X and Y components, if they have any. Okay? Step 4, use Newton's second law. And you're going to do it this way. Sum the forces in the x direction. That will equal ma in the x direction. So you're just going to look in the x direction. And you're going to say, all right, let's add up all the components, all the forces that are in the x direction, and set that equal to ma in the x direction. That'll give you an equation that you can use to solve problems. Sum the forces in the y direction equals ma in the y direction. Sum the forces in the z direction will equal ma in the z direction. Again, you probably won't have to do this very often, but you might have to do both of these. step 5 is solve for the unknown. Okay, so this is the procedure we're going to use to solve lots of problems. Now, before we actually get to that, I want to name some of the forces. We have kind of some shortcut names that we give to forces. And they don't really, there's, unfortunately in the textbook, there isn't just an out-and-out list of them. In the regular physics book, there is. But I'm gonna list them over here. So anyway, this is really important, and I just call it the procedure. And you're going to hear me say this: hey, follow the procedure. Follow the procedure. Don't skip any steps. If you skip steps in problem solving here, you're going to cost yourself more time. Don't think that skipping steps will save you time. It won't. All right. Here are the forces. These are the forces. All right. We're going to have what are called F sub g, or sometimes W. I don't like using W because later on we're going to get to work. I think the textbook uses W with a vector hat on it. That means weight. This is really the force of the earth acting on an object, which we did with the eraser, the force of the earth on an object. But we're going to, I'm just going to call it F sub g. So this is weight. Now, here's, I think our book uses lowercase, they use lowercase n. Now, those of you who took regular physics last year, we used F sub n. This book doesn't do that. It uses lowercase n for this. And this is what's called a normal force. Okay, a normal force is this. If I've got two surfaces that are pressed together, okay, it is the interaction force between these two surfaces that are pressed together that are perpendicular to those surfaces. Lift up the camera here. So here are my two hands. I'm going to press them together. There is a force. See that, here's the surface of my hand here. Surface of my hand here. It's the force when I press them together. It's perpendicular to those forces, like that. Okay. So my fingers are representing the direction of those forces. The word normal in mathematics is another word for meaning perpendicular. And I don't know why they just don't call it the perpendicular force. But when you have two surfaces pressed together, you have two components to that force. You have a force, the component that is perpendicular to those surfaces, we call that the normal force. The component that is parallel to the surface, we call that the friction force. And we're going to get to friction later on, probably next week. But right now, when you have two surfaces that are pressed together, it's called a normal force. We have a capital T, that's a tension force. And this is the force applied by a chain or a rope or a string. And the direction of a tension force is always in the geometric direction of the actual string or whatever. I mean, the direction of the force and the direction of the cable or whatever is the same direction. Here's, let me zoom all the way out. So here's a little cable, and all you can do is pull. We're having a little tug of war here, okay? So the direction of the force is along the direction of the cable itself. And it's always a pulling force. I come from a little town where they use expressions, and there's one, it's like, can't push with a rope. All right. And that's an expression they use, like if you're using the wrong tool for the job, someone will just say, well, you can't push with a rope. And here, I'll show you. If you try to push with the rope, it just doesn't really work very well. All right, so so the tension force is always in the same direction as the object. Now, I think for right now, those are the forces that we're going to be using. There's also just some generic force. I'll call it F sub A. And usually F sub A is either a tension or a normal force. But I use this a lot. F sub A means an applied force. And an applied force just means, hey, you're pushing on a cart or something, okay? All right, it is time to work a concrete problem, and I only have about 6 minutes left to do it. But what I'm going to do is I'm going to apply the procedure to this. Now, your homework tonight is to do the examples in the book. And I really want you to spend a lot of time working those examples. This is going to be a time-consuming period in AP Physics, even more than usual. Okay? But you have to get this stuff. Let's look at an example problem of my own making. So here's an example problem, and I will use the procedure. I'll just start off with the given. I'll just write the problem with given. But I mean, a textbook, this will be written out in a paragraph, and you'll have to do this part. Here we have a horizontal surface. Here we have a big old crate. We love crates. Physicists love crates, okay? Now, what I'm going to do is I'm going to put little magic wheels on this because we're not going to deal with friction yet. So there's no friction. No friction. Oh, fricton. No friction, okay? And I'm going to say this has a mass of 50 kilograms. It's pretty heavy. And we're going to apply a force to it. Somebody's going to push on it with a force of, let's see, how about 80 newtons of force. Someone's going to push on this with 80 newtons of force. And let's say that its initial velocity is equal to 0. And let's say what we're trying to find is its velocity at t equals 3 seconds. So this is a very typical kind of physicsy problem. So let's solve it. So we've just done the first step of the procedure. Given, find, and solve. Draw a sketch of the problem. Show what's given. What are you trying to find? Now, here's the deal. If you're given a force acting on a massive object, and then it asks for some kinematic stuff, at least for right now, you're going to have to use the procedure. Okay? And which means, because what do we need to know in order to figure out how fast it's going at 3 seconds? We need to know what the acceleration is. And in order to get the acceleration, we need to know, what the net force is and all that sort of thing. So, this is a pretty easy problem. Okay? But I'm going to go through the motions of using the procedure. So the first thing we do, the next thing we do after step 1 is step 2. Step 2 is draw the free body diagram. So here's my crate. I isolate it. I only draw the crate. In the free body diagram, you only draw the crate. There is a force of gravity acting on the crate, which is equal to mg. There is a normal force between the there is a normal force acting between the crate and the ground, so that normal force is pushing up. Now there's no friction, so there's no horizontal component to the interaction between the floor and the crate. Super slippery stuff. Or maybe there's little tiny wheels on there. And then there's this applied force that's 80 newtons. This is the free body diagram. This shows all the outside forces acting on the object. Now we're going to do step 3. We have to draw our x-axis and y-axis. Now, this is super easy. All you do is go like this. X and y. That's it. Because what's true about all three of these forces, do I have to break them up into components? No, because they're all, these two forces are in the y direction and this force is in the x direction. So now we can move directly on to step 4. Well, if I sum the forces in the x direction, that'll equal ma in the x direction. So this tells me what to do. Look at just the x direction. If I add up all the forces in the x direction, what do I get? Look at the free body diagram. There is only one force in the x direction. Do you see that? So this is a pretty easy problem. There's only this force right here. So we have Fa, and that's it, equals ma. Now, we know what this is, and we know what this is. So now we can solve for the acceleration and use it to solve the kinematics problem. So let's do that. So A is equal to the applied force divided by the mass. And this applied force is 80 newtons divided by 50 kilograms. And what is that, 1.8 meters per second squared. A newton divided by a kilogram is a meter per second squared. I'll let you work that out. And now I can do step 5. And step 5 is to solve for your unknown. Well, what's your unknown? The final velocity. So the final velocity is equal to the initial velocity plus acceleration times time. I was given time, so. And the initial velocity is 0, so it's just 1.8 meter per second squared times time, which is 3 seconds. And so what is 3 times 8 is 24. So it's 5.4. Is that right? Meters per second. What is it?
It's 1.6 meters.
Oh, 1.6. I was just testing you. Yeah, 3/5 is 0.6, not 0.8. So, oops. And so what do we get here? This is 4.8. Thank you for correcting my mistake. All right. Now, last thing. Oh, no, you know what? I better stop now. Except, well, I'll do this really quick. If I sum the forces in the y direction equals ma in the y direction. Look at the problem. What is the acceleration in the y direction for this problem?
0.
It's 0. So what does that tell me? Normal force minus mg equals 0. Why do I put the minus here? Because I know it's down. And we'll talk more about that next time. Okay, so this tells me, the normal force is just equal to the weight. Except, of course, the normal force is pointed up. and that's down. Okay, we're out of time, but here's what I want you to do. As you work through these examples, read the examples, apply this 5-step procedure every single time you do one of these problems. Don't skip any steps. That is all.